changed the title of the presentation because the original title was Breathability and Moisture, the Key to Building Performance, which is nonsense in the same sense that ultra-low thermal conductivities are the key to building performance, or zero combustibility is the key to building performance, because the key to building performance is to use a combination of appropriate measures appropriately for a given situation. So one property in isolation can't be the key to anything. So as the title says, I'll talk about breathability. It's difficult to give chapter and verse in 15 minutes. So this will be very much within the context of breathable insulation. If I can get to the next slide. Hooray. So I've given four aspects that a breathable material should meet. Anything that can be described as breathable generally is breathable, and you would expect that because breathability is such an intuitively positive property. But in the context of natural fibers that have true breathability, these four conditions really have to be met. And the first thing is that a breathable insulation adjusts its moisture content to be in balance with the relative humidity of the surrounding air. That it adjusts the relative humidity of the surrounding air to be in balance with its moisture content. And they're different sides of the same coin, but you've got to see each one in isolation because there's an equilibrium there that really helps the system maintain balance. The third point is that a breathable material should be able to bind moisture in a way that's harmless. And what I mean by that is that it binds moisture in a way that stops the water behaving like liquid water, because liquid water promotes chemical reactions and biological activity, which in turn damages building fabric and can prove harmful to health. And the fourth aspect is that it's vapor open, because at the end of the day, we don't want moisture trapped within the building fabric. It's got to find its way out somehow. So the material has to be to allow water vapor to pass through it. Just to give you a sense of scale, a single water molecule passing through the eye of a needle would be the equivalent of a dinghy sailing through the middle of the Pacific Ocean. So when something's vapor open, it can appear to the naked eye to be solid, but in actual fact, water vapor, which is a gas, can move through it. So what sort of materials, insulation materials, are breathable? Well, I've just rattled off some materials there: hair, wool, jute, flax, wood fiber, cellulose, cork. All those fibers are composed of sort of four natural polymers. So you've got keratin, which is the backbone of wool and hair. You've got cellulose, hemicellulose, and lignin, which form the backbones of plant fibers. And these molecules will, sorry, I don't know how close to the microphone I need to be standing. Is that okay? All these molecules will attract water molecules that will stick to them like magnets. There's a deliberate mistake in this for any chemistry geeks out there. I include myself in that. That should be a positive on the water molecule and a negative on the keratin. But the water is just about to dock with the keratin there, and that just sticks through an electrostatic force like a magnet. And some of the water is very tightly bound and never really leaves the natural fiber, and some is very loosely bound and never really sticks to the natural fiber. But there's a Goldilocks zone in the middle that allows natural fibers to absorb and hold the moisture in a way that man-made fibers simply don't. And that's through a process called adsorption and desorption. So adsorption is simply when the natural fiber picks up a water molecule and holds on to it, and desorption is the opposite process, where the natural fiber gives back its moisture to the air, which is then released as water vapor, which is a gas. Water vapor isn't the sort of steam that you see on the top of a teacup. It's an invisible gas, so you can't see water vapor. I can't talk about breathability without putting a sorption isotherm graph in. Essentially what this says is that at a given temperature and a given relative humidity, a natural fiber will want to be at a specific moisture content. If it's out of kilter, it will either give up moisture to the air and increase the relative humidity of the surrounding air, or it will reduce the relative humidity of the surrounding air by pulling water vapor from the air. And that's quite important for insulation, because if you think about it, as temperature drops, relative humidity increases, and the natural fiber then wants to increase its moisture content, so it pulls the moisture out of the air. So it's constantly pulling the relative humidity of the air away from the dew point. The reverse happens when the temperature rises. You can see there's two slopes to this graph, and it's just that when the natural fiber is absorbing moisture, it wants to be at a different equilibrium to when it's releasing moisture. But that's, to all intents and purposes, not relevant, really. That's just one for the real scientists out there. So as I've said, sorption, when I say sorption, I mean adsorption and desorption. And that's driven, when it comes to the natural fiber, by relative humidity, much more than temperature. And that's important because that means that the ability of a natural fiber to absorb and release moisture is, to all intents and purposes, immaterial, not related to temperature. But the ability of air to hold moisture is very much related to temperature. So as temperature changes, without wishing to repeat myself, but as the temperature drops, relative humidity increases, and the natural fiber starts pulling the moisture out of the air. This just denotes the Goldilocks zone I was talking about earlier. So in zone A, it's what's called monolayer water. So this is water that's bound to the natural fiber that you need an awful lot of energy to release. Again, the polylayer water in zone C is the moisture that's very loosely bound to the natural fiber. And that essentially doesn't play much of a role in terms of breathability. When there's that amount of moisture as you go from 0 to 1, the water starts to behave more and more like liquid water. But this zone B in the middle is where the breathability really comes into its own. And roughly speaking, that's between about 10 and 20% moisture content for the natural fiber. So in a kilo of natural fiber, that's the ability to buffer around 100 grams of water, which doesn't sound a lot, but it is an awful lot when you consider the mass of moisture in the surrounding air. So why is breathability important? Well, moisture can contribute to a lot of health and structural problems within the building fabric. There's a well-used graph here that just shows, when bacteria, viruses, chemical reactions, etc., when they start to proliferate and when they don't. And there's a relative humidity zone that's where you really want to keep the fabric to stop these sorts of processes happening. This is something that's very, very well understood in the food industry. The food industry is probably 40 to 50 years ahead of the construction industry in terms of its understanding of the impact of moisture. And there's very good reason for that, and that's that moisture in food causes very acute economic and health problems. Moisture in buildings causes very chronic problems, and we're hardwired to ignore chronic problems until they become acute. So this is a lot of proven science here that sort of transcends construction. I used to have a presentation that demonstrated this very effectively using a Jaffa cake, but it was just a little bit too abstract, so I don't do it anymore. Why are breathable materials important? Well, I think there's a sort of well-referenced paper on breathability being a red herring, and in that I think it was said that breathability is a red herring because 95% of moisture is removed through ventilation, which I wouldn't argue with. Some people would say it's lower, but what about the other 5%? You know, the other 5% equates to about 2 bathtubs of water unaccounted for within the building fabric every year. In my mind, that's not an insignificant amount of water, so we should give consideration as to how that's dealt with. And getting back to my opening remarks, to say that one thing is the key to any level of performance is an absolute nonsense. So to disregard breathability on the basis that something deals with 95% of a risk wouldn't be acceptable in the food industry, because you wouldn't eat food that someone told you was 95% safe when it comes to salmonella or other spoiling. So why would you take it when it comes to your building fabric? What we need to do is to do what the food industry do and use a combination of measures that includes breathability. I'm not going to sit here and say that most moisture isn't dealt with by ventilation, because that would be ludicrous. But it doesn't deal with everything. That last slide just shows hurdle technology, which again is quite common in the food industry, where you just look at the various measures that you need to put in place to get to, say, 99.9% effectiveness rather than 95%. So if we set the bar a bit higher, maybe people will think about these things a bit more. And on that note, thank you.